Hello and welcome to MiniLecture 23 on equilibria. All right, so in the last lecture, we talked about differential equations and initial value problems, also known as IVPs. In particular, you guys looked at an IVP of tuberculosis, the dynamics of tuberculosis incidence, T of T, over time. We had this differential equation here, so you have some infection in the model and some recovery. Infection, incidence increases, recovery, incidence decreases. In particular, we show when r is equal to 0 that this is a solution to the differential equation. All right, if I plug in beta equals 0.005 and n is equal to 100, we have that we have these dynamics of tuberculosis incidence. So over here I have RT of T, and down here I have time. So where is our initial condition on this plot? This is the initial condition on the plot. All right. So in this lecture, we're not going to be looking at this initial condition. We're going to be looking at the equilibria of the system, or the equilibria of the IVP. The equilibria describe the possible, I'm going to emphasize that word possible, the possible long-term outcomes of this system. In particular, I'm going to tell you that there's an equilibrium in the system around there. All right. So in order to find the equilibrium, what we're going to do is we're going to take our differential equation df dt and set it equal to 0. So in this case, we're taking dt dt and setting it equal to 0. And we're going to solve for f. So solve for f. So solve for the state at which the system is no longer changing. This is the change in the system. When is that change in the system equal to 0? That will be a long-term outcome. All right. So let's go find all of the equilibria of T of T here. All right, so we start with our differential equation. dt dt is equal to beta n minus r times t minus beta t squared. And then we're going to take that differential equation and we set it equal to 0. All right, so since we set it equal to 0, it's no longer a system of time. So let's get rid of the time. So we have beta n minus r and we have t hat. So this is the long-term outcome. It doesn't describe the dynamics at any given time, just in the long, long time. So we make it a t hat instead of a t of t. And we set that equal to 0. All right, so when you have a differential equation, I always want you to look for the case when the equilibrium is equal to 0. This is known as the trivial solution because it's kind of a boring solution. All right, what happens if t hat is equal to 0? Well, then this term will go to 0 and this term goes to 0. So we have 0 minus 0 equals 0. That works out. So this is indeed an equilibrium of our system. All right. That's all well and good, but it's not necessarily the only equilibrium of our system. So let's go find the other ones. All right, so we have t hat minus beta t hat squared equals 0. All right, I'm going to multiply both sides of this equation by 1 over t hat. If I multiply both sides by 1 over t hat, this is going to cancel with that, and it's going to cancel with one of those squareds. Remember, you have to multiply that through all of the terms, and if you multiply by 0, it's still 0. So I end up with beta n minus r minus beta times t hat is equal to 0. All right, we're trying to solve for t hat here. That is the key. We're trying to solve for t hat. How do we do that? Well, we're going to move this over to the other side of the equation. So we have beta t hat plus beta t hat. And then we're going to divide both sides by beta. So divide by beta, divide by beta. What I end up with is I have t hat is equal to beta times n minus r divided by beta. All right, so this is our second equilibrium of the system. All right, so let's go draw these two equilibria on that plot up above. The first equilibrium is at 0 here, and the second equilibrium is at 100 and something. It's up here. So this is the beta minus n divided, what was it again? Beta n minus r. Beta n minus r divided by beta up here, and here is our 0. So here are the two possible outcomes of our system. There's one outcome down here, and then there's one outcome up here. All right, what do these two outcomes mean in words? Well, if we have the t hat equals beta n minus r divided by beta, this is when tuberculosis is endemic in the system. It persists forever and ever and ever. It's an infection that exists forever. And then we have t hat equals 0, and this is known as extinction. So if tuberculosis goes extinct, then the incidence of tuberculosis is going to be 0. All right, so what do we do? What are some other things we need to know? Well, we have to know that not all systems have equilibria. Not all systems stop changing at some point. All right, so consider this simple differential equation. For bark growth, you have the thickness of the bark, and it's growing at some constant rate, g. It has some initial condition, b0 equals 1. This is our initial value problem that dB dt is equal to g, and b0 equals 1. All right, this is the solution to the differential equation. If you want to use this to double check that this is a solution, go ahead and do that. All right, so let's look at this, the equilibrium. We have dB dt is equal to g, and we're setting this equal to 0. Remember that this is no longer a function of time because we have now set it equal to 0, so we're going to replace all the b's with hats. All right, but there are no b's here, so all we have is that g is equal to 0. G is not a function of b hat. This means there does not exist a b hat for which dB dt is equal to 0. This implies that there is no equilibrium. So we're not trying to find the values of the parameters, like the parameter g, where this is true. There is a parameter g which is true, which is g equals 0. But there is no value of b hat for which there is equilibrium. And as a result, as long as g is positive, we see that bark thickness just gets bigger and bigger and bigger and bigger. All right, with that, I'm going to leave you with this self-study question about gout, where you're going to try to find the long-term outcome or the equilibria of the quantity of uric acid.